обычно я запустил трансляцию, посмотреть просто, что там, если не так. Вы убьете, что не так. Если неправильно настройки этой камеры. Тебе должны там. Okay, so the goal, first goal for today is to prove growth and trigonometry theorem, and for this we need the following lemma. So let, as usual, Rm be a local Noetherian ring. Let's take n to be a finite R module. And let's also fix notation for the dimension. So D is dimension of this module. So then I claim that the maximal ideal is not associated with the following module. We have local homology of degree D, maximal ideal for the module M, and then dual. So maybe looks like a not very interesting statement. It's like a technical lemma that we need to prove the next theorem. Okay, so first of all, it's easy to see. I'm going to leave this as a little exercise that we can assume that R is complete. So this condition is satisfied for R if and only if the analogous condition is satisfied for the completion of the ring. And then we can consider the following. The following short exact sequence. 0, gamma sub m of f, this is embedded into f, and there is a quotient. I'm going to denote quotient n prime. So n prime is just by definition quotient of the n by this m torsion submodule. So then the first observation that I claim is true is that if I look at the local homology, say with index a of n and the same local homology for the n prime, they are the same, isomorphic, and that is for any k greater than 0. Okay, so the question is, do you see why this isomorphism is true for local homology?
Because there's 0 for the leftmost.
Yeah, that's the equivalent way to say this, but why they are 0 for this one?
Because it is M torsion.
Yes, and still. Why all higher local homology for M torsion is 0?
But we have proved it.
Yeah,
I think yes.
I don't remember doing something with this, but maybe I'm wrong.
In corollary 3, before section 5.3.
Maybe indeed prove this. Yeah, but actually I was thinking about different proof that you can derive this from one of the exercises in the assignment. So for example, if you know that you apply this functor gamma to the injected module, you still get injected module but I torsion. And then you can kind of compute the corresponding I torsion injected resolution of the gamma. It's kind of identity factor. Okay. Don't need this, it's a little bit longer. If you already know this, it's fine. Okay, so we have this. Yeah, and also, of course, we have that. So we have this, and then let's look at the support. So the support of the M is the support of the M prime union with the support of the gamma sub M of M, but this is just supported on the maximality. So this is zero dimensional. Hence, the dimension of the N prime is the same as the dimension of N. Well, let's say this is positive, right? I want this dimension and this lemma dimension to be positive. This is zero.
Why the dimension are the same?
Well, the supports are more or less the same up to and adding a close point, right?
Yes.
Which is just a zero dimensional. So just topologically, dimension has to be the same. It's supported on the closed sets. The difference between these closed sets is just one point. So
Yes.
dimensions has to be the same. Okay, so dimensions are the same. And now we also know the following, since we can say that the zero slope of cohomology, or just write gamma, of the n prime is zero, right? Again, this is from the long exact sequence. Zeros homology of this thing and this thing is the same. So for the n prime it is a zero. So these are zero, and from this we get the depth of the n prime is at least one, right? This is by the property, we know that below depths everything is zero, and for the depths it's definitely not zero. So if h0 is zero, then definitely a depth starts at least with one. So, but if the depth is at least one, so there is at least one regular element. So there is W in the maximal ideal, regular on the module n prime. Now let's look at the part of the long sequence for the local cohomology. So I want to write HD. So yeah, the n prime quotient by the W n prime. Well, I'm not writing the short exact sequence, but this is just first we have the short exact sequence 0 n prime W n prime quotient of the n prime with the W n prime. And this short exact sequence gives us long exact sequence of local homology. HD n prime. Yeah, and I also, on the same picture, want to take those, right? So if I don't take those, the map's supposed to be in that direction, but if I take those, I think now what I have is correct. So here, of course, this is just induced by the multiplication of W, which is still multiplication of W. Okay. Now, this module, right, so we take a quotient by one regular element, so the dimension of this module that we have here is d minus 1, right? And we look at the local homology at index d, and we know that this is definitely 0. We prove that the local homology is 0 if you go higher than the dimension of the module. So this is 0, and this means that W is regular. Is regular on the module that we consider, namely H, D, M, and prime. But let's do, right? But if we can find at least one regular element, then we can say that maximum ideal is not associated. The HD and right. I'm kind of doing two steps here. I know that if there's regular element m is not associated, and also at the same time replacing n prime with the n, still the homology are the same. Okay, that's the end of the proof. And
Why it is not associated with cohomology related to n rather than n prime? So why we delete prime?
this not the same homology.
Oh, okay.
Okay, so theorem, sometimes it's called Grothendieck non-vanishing theorem. So let Rm be a local Noetherian ring, as usual. M is a finite R module. Let's say that D is the dimension of M. In this case, it could be 0. So then the top of cohomology, so the cohomology with the index D, where D is the dimension of M, is a non-zero module. Okay, proof. Well, again, without loss of generality, R is equal to the R with the hat, so R is complete. In this case, this is trivial. We know how the homology for the R completion for R are related, so clearly they are non-zero if and only if they are non-zero for the completion. So the proof will be by induction on D. Okay, so let's consider first a case when D is equal to 0. So, do you see why this statement is true, but the D is not, the way D is 0? It's supposed to be an easy case.
Because the depth is 0 and we know.
Yeah, you can say that in this case, well, definitely in dimension 0, everything is going Macaulay, depth is the same as dimension. So we know that for the depth, this is definitely not 0. Also, you can say something like this: if the D is 0, it means that M is 0 dimensional. It means M has a finite length, right? And if this is finite length, essentially what we need to show is that the gamma M of the module finite length is not 0, but we can actually compute this gamma M is just M itself, right? The module itself, because if this is a module finite length, and that any element is annihilated by some power of the maximal ideal. So in this case, we actually know the answer. So then let me write it like this. And then H0 of M is just equal to M, hence not 0. Yeah, maybe I need to say just to avoid kind of trivial cases that, of course, in this statement I assume that M is not 0. And I guess in this case I also need to assume that I have a non-zero module, but this is just a silly remark. I think it's also useful, before we do the step of the induction, to consider the case when D is equal to 1, kind of consider this separately. Not necessarily to do this from the point of view of the logic of the proof, but you can kind of see how it works in this dimension and just generalize this for the step of the induction. So in this case, so if D is equal to 1, consider a short exact sequence, the standard one. We take M torsion, which is a module in M, and the quotient we're going to call M prime, as in the lemma. So as in the lemma, we notice that the H0 of the M prime is 0, hence the depth of the M prime is at least 1. Right, but also we know that the depth of the M prime is always bounded by the dimension of M prime. And again, the same reason as in the lemma tell us that this is the same as dimension of M, and we consider a case where this dimension of M is 1. So the depth of M prime depth is at least 1, and it's also bounded by 1. So the only possibility for this is that the depth is equal to 1. So depth of the M prime is equal to 1. And if the depth is equal to 1, now I get the same reasoning as in the lemma. H1 of M is the same as H1 of the M prime, but the last local homology is not equal to 0, because we know for the depth this is not equal to 0. Okay, so let's try to generalize this for the step of the inductions. Now suppose that the D is greater than 1. So clearly the same argument works as in the D equal to 1. So I can conclude that as before, without loss of generality, I can assume that the depth of M is positive. Right? So I'll do the same. I think I consider the short exact sequence and go from M to M prime. And if I can show this for the M prime, I'm done, right? Because the cohomology for M and M prime are the same. So without loss of generality, I can start with the module with the positive depths. So if the depth is positive, I can find element, let's call this W, in the maximal ideal regular on M. So consider short exact sequence, the standard short exact sequence, M multiplication on W to the M, and then there is a quotient. And now let's look at the corresponding long exact sequence of homology, and I also going at the same time take a matrix dual of this long exact sequence as in the lemma. So HD M dual HD minus 1 sub M of the M module WM dual HD HD minus 1 so here's W HD minus 1 M 2. I hope this is correct. Yeah, it looks to be correct. Okay, so this is what terms of this long exact sequence. So by induction hypothesis, well, I can assume that the HD minus 1 of the M modulo WM is not equal to 0. This is the statement for the D minus 1. Okay, now let me assume that local homology with the index D for the module M is 0. I want to derive a contradiction from this. So then I claim that the following is true. If I take a complement in the maximal ideal to the union of all the prime ideals, so prime is associated to the module M, then what I'll get is the union of the prime ideals Q, and this Q that I have here is associated with the module HD minus 1 of M and then 2. Okay, do you see how I can see this from this this part of the exact sequence? Well, I assume that, what I assume? So I know that this is 0, right? If I assume that this is 0, so then this is 0. So yes. Yeah, that's right. So essentially, I'm taking this W, right? This W is in the maximum lighting. And I know that this W is regular, right? So, meaning this is regular, it is not a zero divisor on M, and the zero divisors are here. So I'm taking W kind of from this set. And when I know that this is 0, I look here and I see that this W is regular on this module, which is local cohomology, right? And if this is regular, right, so this is not in the zero divisors, and again, zero divisors are here. So hence I have this inclusion. Equal.
I don't know. I don't understand. We take W regular on it lies in the left-hand side, and we conclude that it is not a zero divisor of the cohomology in degree d-1. So it.
I think this wrong. This is not 0, right?
Yes.
So it means that this, and if this is 0, so we have a 0, something definitely not 0 in this W. So this W is definitely not regular. So this is definitely zero divisor. Hence,
yes.
it is here.
Yes. Yes.
So,
Okay.
all this makes sense. Yeah, I just confused myself a little bit, so somehow I decided this is 0. This is definitely not 0 by the induction hypothesis. Okay, so we have this. So we can conclude. Notice that we have finite module, and this is also finite module. So these two unions are finite unions. So we can use prime avoidance to conclude that M is either associated to M, which is not possible, right? Since we know that the depth of M is positive, or the local homology with the index d-1 of M, and then that is global. So the possibility here is that this M is associated to this module, right? Now, last observation: any element of the h(d-1) of M of the module large M matrix dual, so which is annihilated by the maximum ideal, is annihilated in particular by the element W. Hence, while looking at that part of the exact sequence, this element comes from the h(d-1) sub M of the M quotient by the Wm dual. So M is not just associated to this module, but to the module, okay, associated to the h(d-1) sub M of M virtual Wm dual. Right, if this is associated to this is in fact associated to this. Now looking at the exact sequence. But this is a contradiction with the previous lemma. So that's not possible.
Can you repeat, please, the last paragraph?
Yeah, so before I get that the M is associated to this module,
Yes.
I want to derive from this that actually M is associated to this module.
Yes.
Right? To get the contradiction in the lemma.
Yes.
So now this quotient will be N in the lemma. So this is the dimension d minus 1, so apply this lemma for the d minus 1. So just a second. If I apply this for the d minus 1, actually this makes sense, right? Because this step is for the d equal to 1, this step is necessary, right? Because otherwise the induction won't work. Well, this would be H0. But anyway, so everything is fine. So what I'm saying here is that, of course, if the element is annihilated by the maximal ideal, this is annihilated by some element of this is annihilated by the W, right? So if I'm saying that M is associated with this module, right? It means that this annihilates some element
Yes.
in this module, right? But if any element in the maximal module annihilates this element in this module, in particular, this W annihilates this element in this module. Hence, there's an element kind of from here that is mapped to this element.
Yes.
And this element, of course, will be annihilated again by the maximal ideal M, and hence the maximal ideal M is associated with this module.
And why this element will be annihilated by the maximal ideal?
Oh, well. Think about this. Why this is annihilated by the maximal ideal? Maybe it's not so easy to see this directly. Well, but at least what I know by the assumption that this is 0, right? So this will be a sub-module here. It means that the associated primes of this module is a subset of the associated primes of this module.
So it is simply a submodule, and of course, its annihilator is maximal ideal, because it doesn't depend in what module to multiply by an element from the ring.
Yeah, so the observation is, since this is 0, this is the sub-module. Yeah, we can compute annihilator in the sub-module in the module. Okay, but that's the end of the proof, as you can see. I really like this proof. If you look at the proof, the bronze and Hertz, the proof there is much more complicated. It's in another situation where you have to rely on the coin structure theorem. You go to the complete ring, you use coin structure theorem and do some little bit longer computation. So this is kind of nice and short argument. Okay. So that was the kind of hard theorem. Now we're going to derive several easy theorems, not related immediately to this one, but still we are in the situation where we have a local Noetherian ring. So Rm is a local Noetherian ring. Let's say that the M is dimension of Rm is an R module. So then I can write the following formula, that the local cohomology with the index k and the maximal ideal M of the module M isomorphic to the Tor with the index n minus k. First argument is M, and the second argument are local cohomology, the top local cohomology for the dimension, which you know are not equal to 0. Okay, so the proof is just more or less immediately follows from what you already know from the previous lecture. We take x1, xn in the maximal ideal to be maximal regular, say R regular sequence. So it is a system of parameters. So the maximal ideal is the radical of the ideal generated by this sequence. And I know that the local cohomology I can compute using this ideal generated by this sequence, since the radical is the same. And for this sequence, I know that I can reduce my computation to the Tor. Wait, I missed one condition in the statement. Maybe you can see what condition I'm missing to derive this formula. It won't be true for any local Noetherian ring. Yes.
Maybe it should be Cohen-Macaulay.
Yeah. Well, I want this to be a regular sequence, right? But this is, well, as I said here, but this will be a regular sequence, which is the same thing as a system of parameters, if this is a Cohen-Macaulay local Noetherian ring. So for Cohen-Macaulay, we have this general formula that the local cohomology can be computed as a Tor. And notice that this is one of the rare statements where M is not necessarily finitely generated. Okay, now I want to specialize this statement to the case of the Gorenstein rings. And for this I need lemma. So lemma, let Rm be a local Gorenstein ring n is the dimension of this ring. So then I have an answer for the local cohomology, say Hi of this ring. So the answer is the following. This is the injective hull of the residue field if I is equal to n and 0 in all other cases. So the proof was just direct computation with the minimum objective resolution. So let E with a bullet of R the minimal objective resolution of the ring R. So then we know that if I'm interested in the term in the index I, this is just the sum over the all prime ideals of the height equal to I, injective hulls of the R module E. So if I apply counter gamma sub m to this resolution, I'll get a very simple complex. In this complex, I'll get zeros everywhere except position n, where I am getting residue field, injective hull of the residue field. This kind of computation that we've done last time. So, hence the result. We only have top local cohomology which are equal to the residue field. Okay, so corollary from this proposition and this lemma is the following. So let us before Rm be a local Lorentz ring. And is the dimension of this ring M is a finite R module. So then local homology HK of this module are isomorphic to the door. Well, wait. So in this statement, I don't need this to be finite, so I can remove this. Yeah, isn't just an R module. So door n minus k m e. Okay, so I don't need to prove this really, just the previous statement where for Gorenstein situation I explicitly compute the topological homology. And immediate corollary from this one is that if I again assume the same assumption that this is a local Gorenstein ring and its dimension of R. Now I need that M is finitely generated, so M is finite. So then the formula for the local homology will be text n minus k, right? N minus k, M, R, and then rho. Okay, so this is just the previous corollary that I combine with the second version of the XOR duality, right? For the second version of the XOR duality, I need a resolution of finitely generated projective modules for M, but this is true since R is not even and M is finite. So this last statement, so this last isomorphism, usually called the local duality. Probably one of the most famous theorems about the local homology. There are not so many important states about local homology. Probably one important statement is that it reduces to the stabilized Kazoo complex, inverting deconvolution theorem, and some forms of local duality. You can see in this case we get this only for Gorenstein rings, and for Gorenstein rings it's kind of looks very nice. It's so simple formula. Yeah, so next section, and this will be the last section in this chapter. So 5.4. Well, not, yeah, probably I'll have one more section. So let me call this local duality and canonical modules. So the goal is to generalize this nice formula for Gorenstein rings for all Cohen-Macaulay rings, local Cohen-Macaulay rings. For this, I introduced the following definition. A canonical module of a local Cohen-Macaulay ring is a finite R module, okay, such that the top local homology of the ring R is just the matless dual of the K, right? If you look at this, how we derive this local duality for Gorenstein rings, you can see that I'm kind of choosing definition in the way that local duality is more or less satisfied by definition. So let me just state this immediately. Theorem. So this is local duality. So let
Yk is finite. Yk is finite module.
Well, this is a problem with the notation. This is not a field, this is just large K.
Yes, y is a finite module. So we defined it as matrix dual to cohomology in grid.
Yeah. And then this agrees nicely because
it is Artinian.
yeah, this is Artinian. For example, if you have a complete situation, you can kind of, well, you know that this too, everything will be reflexive. This is Artinian, this is finitely generated. So you can say that the K is just kind of the dual of this Artinian, so it has to be finitely generated. But this is not the complete situation. We cannot say this. So we can just give a definition that we have finitely generated modules such that matrix dual is the same as this.
So in general, it may not exist.
Yes, that's a good remark. In general, there are no reasons to expect that there is a canonical module. And in fact, there's a theorem that there are examples, say, in dimension 2 of the Cohen-Macaulay rings without canonical modules. But, of course, as I mentioned, in the complete situation, any Cohen-Macaulay ring has a canonical module. So the theorem is kind of that there is a local Cohen-Macaulay two-dimensional ring without without canonical module, but it's kind of not explicit. You cannot just write this kind of in terms of what it is. You can write what its completion is, but not for the ring. So if you're interested, you can send me a mail and I give you this paper where this is discussed. It's not very easy, so I'm not going to do this in the course. Yeah, so local duality. So let this thing be Cohen-Macaulay local ring. Let me fix D to be dimension of R, and we suppose R admits a canonical module. Let's call this K. Then for any finite R module M, we have the statement of the local duality, that the local cohomology with the index K of the module M is isomorphic to the X with the index D minus K M canonical module matrix 2. So that is a statement of the local duality, and sometimes in the literature you can find kind of variation of this statement where you move this matrix 2 from the right hand side to the left hand side, and then you need to write something like completion of this X module with respect to the M. Okay. Of course, I don't want to prove this because, well, the proof will be more or less the same, just a second version of the X-tor duality plus this general formula of the stop local cohomology. And so I want to mention that we kind of get this local duality for free without any proof. If you look at the literature, it's not how usually things work. Usually people start with a dualizing module, right? And sometimes people start with the dualizing module and then call this canonical module, so it's kind of a mix of the notation. So my goal is now, using this definition, derive some elementary properties of the canonical module, then introduce the notion of the dualizing module, and then show that the module is canonical if and only if it is dualizing. So then, in this way, we get kind of the standard formulation of the local duality with the dualizing modules. Okay, so before we do this, I need a general. The first goal is to show uniqueness, right? So from the definition, it doesn't follow that this large K is unique. So I want to show that this is actually unique. And for this, I need a general property of completions. So let me say that, as usual, I have a locomotive ring. Locomotive ring. I have M and N are finite are modules. So if the completions of these two modules are isomorphic, then these two modules are isomorphic. Technical statement about conclusions that we need to derive the uniqueness of the canonical module. Okay, let phi with the hat be an isomorphism. So from the M to the N. So this is an isomorphism. Now we can notice that if we look at the home over the completion between two completions of the finite generic modules, this is isomorphic to the home between these modules, and then I take completion. So if you don't know this formula, recall that there's such formula for localizations, and there's a little bit more general statement where I take it as a product with a flat ring extension, and reduce this to the 5 lemma, and do this. So, exercise. If you have problems, but I doubt that you have problems with such, I think you can look how we can prove this for the localizations, and the statement of localizations in the lecture of the Wolfram. So I'm just going to use this. Okay. So I have a publicly that there is phi 0, which is in the home over R from M to N, such that phi hat minus phi 0 completion is in the M hat home over R hat, M hat, N hat. So I'm kind of choosing representative of the phi hat modulo M hat. Right, and then I use that if I take a quotient of a module of the, instead of this module, I can think about this module, and if I take a quotient by the M hat times this module, it will be the same quotient as this module, modulo M. Hence there is a representative that lives here. Okay, so now we have log exact sequence. So this is phi 0, back from M to N. Q is the cokernel of the phi 0. So this is by definition. And this is the sequence exactly on the right. So then we can take a tensor product of the sequence. So let's take this tensor product R modulo M, or the same thing as the tensor product with the R hat modulo M hat. So then we'll get the following M modulo M. Then I'm going to call this phi 0 with the bar. So it's kind of reduction of the phi 0 modulo the maximal ideal. So M modulo M, N. And finally, U modulo M. Okay. Now I can notice that the phi 0 with the bar, so reduction modulo the maximal ideal, is the same thing as I take completion first of this phi 0 and then take reduction. This more or less follows that the quotient of the R modulo M and R hat modulo M hat is the same. but I know that the modulo maximo ideal, this is the same as the reduction of the phi hat without zero, right? And this pi hat is an isomorphism, so its reduction is an isomorphism, so Q modulo MQ is isomorphic to zero by Nakayama's lemma. Q is isomorphic to zero. Okay. Now let me say that there is also map psi. This is map from the n hat to the m hat, which gives an isomorphism. So this is inverse for the phi hat. So the position of the psi hat and the phi hat is the identity of the m hat, and the composition in the other order is the identity of the n hat. Well, we just repeat this procedure, but now for the psi instead of phi. So in the same way, we can get psi 0 from the n to m. Such that, well, we prove that the phi 0 is an epimorphism, so psi 0 is also will be an epimorphism. In particular, the composition will be epimorphisms. So psi 0, phi 0, that is a map from the m to m, and composition in the other order, phi 0, psi 0, from n to n. These two maps are epi. Hence, by statement that you can derive from the Nakayama's lemma, if you have endomorphism of a finitely generated module which is epi, in fact this is isomorphism. So, well, if you haven't seen this, you can find this in the lecture notes on the Google Drive, but the conclusion is that the psi 0, phi 0, and phi 0, psi 0 are isomorphisms. That's all we need to show. Okay, so corollary. So let Rm be a local Noetherian ring. Oh, Cohen-Macaulay actually. Cohen-Macaulay local Noetherian ring. If a canonical module exists, then it is unique up to isomorphism. Well, I think this is now easy to show. So let K and K prime be canonical modules. So then completion of the K we can identify with a double dual of the K. This we can identify with the local homology, top local homology of the R dual. And now we just do the same thing for the second. So K prime, double dual, which we can identify with the K prime completion.
Why K double check this car completion?
Now, let me again do this as a little exercise. You know this for rings, right? Then you can derive this for any finitely generated module, or you can see this for any finitely generated module. Like for example, again, you take a finitely generated module, take its free presentation, apply this functor, use 5 lemma. Okay, so if it exists, it's unique, and for this reason, people have notation. So they just write K sub R is the canonical module of R. But you can again notice that this theory is not completely satisfactory. The canonical module, it's unique isomorphism, but it's not canonical. So you still have some choices. You can kind of improve this theory a little bit. You can try to construct factorial theory. It is possible, but it requires some time to develop this. So I'm not going to do this in this course. Okay, now I want to derive a bunch of elementary properties of these canonical modules. So instead of repeating in every proposition that I'm going to prove what my assumptions are, I'm going to say the following. So in propositions below, Rm is a local Cohen-Macaulay ring. I'm going to use this fancy notation for the residue field just to avoid the confusion with the index in homology. And also E will be, of course, the injective hull of the residue field. So D always will be dimension of the R. And of course, as I introduced before, case of R is the canonical module. Okay. Proposition. Finite module K is a canonical module for R if and only if completion of K is a canonical module for the completion of the ring. Well, that's a very useful proposition, so we can reduce some proofs to the case of a complete ring. I think it's easier. Proof. Okay. Well, first suppose that K is a canonical module for R. So if we know that the dual of K is isomorphic of the HD and R, then again completion of K is isomorphic to the double dual of K, and this I can identify with the matchless dual of the top local homology. So then, if I apply matchless duality one more time, I'll get completion of K dual now is isomorphic to the HD sub M of R double dual. Now this is isomorphic to the home over R hat of the local cohomology of R tensor product is the R hat ER, so just E dual. Well, let's discuss the last isomorphism. So of course, it's just the second dual doesn't do anything. So essentially, I need to understand why the dual to this thing is the same as this home.
Because both E and local cohomology are models of a head.
Yeah. Now this is the way to see it. Oh, and probably you can see this just more or less equivalently by saying that we have home tensor adjunction, right? You have this home over R hat from this tensor product, right? You can write this as a home over R from this module, and then you have home from the R hat to the E, which will be just again E. Okay, so we have this isomorphism. Now, of course, we can notice that this tensor product is precisely so still home over R hat, and instead of this tensor product, I'm going to write top local cohomology with the completion of the maximal ideal for the completion of the ring E dual. Right, but now this is just a double dual of the local cohomology, which is Artinian, so it's matless reflexive, so this can be identified with just the local cohomology over completion of the ring. And that's what we need, right? I take the completion of K, take its dual, and say that this is local cohomology of the completion. So this proves the statement in one direction, so let's go in the other direction. So conversely, if we know that the K completed and then dual is isomorphic to the HD M completed R completed, well then I can write that the triple dual of K is isomorphic to the HD of MR double dual. Right. So here I just rewrite the completion as a double dual on the left hand side. On the right hand side, I use the formula that I just proved, that the double dual of this local cohomology is precisely this local cohomology, so I just plug this formula back into my isomorphism. Well, but from this, we can derive that the K dual is isomorphic to the HD sub MR. Right, so if I take double dual and get something isomorphic, then the original modules are also isomorphic. Okay. So this is.
Why is this so? We have to take a double dual and get in isomorphic models. We initially have isomorphic models.
Well, I can rely on the proposition that I just proved, right? I can sure, wait a second. Well, not really. I wanted to say that the double dual is the completion, right? But unfortunately, this thing is not a finite module, so it won't work precisely. Well, what else can we do here? think what we can say is that at least we have a maps in one direction and the other direction, right, between those two modules.
Why?
Well, that is because, well, these are functors, right? So, if I think about this double dual, in fact, what double dual is just a tensor product with the R hat, right? So you have a home between, if I take a tensor product with the R hat and have a map, can I move it back?
So applying double dual is simply taking a completion.
Well, it will be taking a completion finally generated, but I think in general it will be tensor product with the R hat. Well, that is because, well, if you do this again, if you do this for the, well, we need to be accurate if it is not finally generated. If it is not finally generated, this is, I think, more over true. No, but that's, well, if we look at the home from, say, from this thing to this thing, right? Then apply Matlab's dual to this home. Right, so we will get a map from the home, from between those things to the home between Matlab's dual in the other order, of course. Then you apply the home Matlab's dual one more time, and we will get a map between homes. Now the question is, can we pull back this isomorphism to get a map between those modules? Because if you can pull this map, then we can look, for example, for the kernel and kernel, then the kernel to kernel by the double duality is mapped to the zero module. And since we have a map into injective cogenerator, it has to be zero itself. So there is no kernel to kernel. So I think the only question is when we look at the home, say from here to the H, G sub M, R, to the home K triple dual, H, D, M, R, double dual. Can we take this isomorphism that lives here and pull it back as a map between those two modules? Or in the other way, it doesn't really matter. We can switch the order. Also looks like, well, probably to get this, the computation that you need to do is somewhere hidden in these two lines, just somehow going in the other direction. Maybe we can do this simpler without this. But in general, is this true that if like home to the injective cogenerator is the met on the homes epimorphism? Because if you have this, then the composition will be epimorphism, and that's enough. I don't see the moment why this has to be an epimorphism. Okay, maybe we can try this without this triple glue. So, what we have here is the K, then the product is R hat. Let me maybe write this with the home to the E, right? So this is the left hand side. And the right hand side, we also know that this is H D sub M of the R, then the product with R hat, right? So this is over R. Alright. So by adjunction, this we can replace by the home over R hat. K, and we have home from the R hat to the E. Then this is isomorphic. No, this is isomorphic for the same. Okay. Of course.
Maybe it is over R, not R.
Here?
Yes. Because
Well, by the adjunction, I think it has to be over R hat. The adjunctions with the home and tensor works.
but K is not a module over R hat. It is R module.
Yes, but then home over R here, but then for the adjunction to work, I still need to put another link in the home, so probably something like this is true then, home over R hat, right?
And the second argument is simply E, because C is a R hat module. Is the second argument.
Here?
Yes,
Yeah,
equal to.
so this is of course can be identified with the E.
So we get K2.
Yeah, we have K dual, yes. But it can be correct. Can it be?
And on the right we have also local homology, because they are module of error completed.
You can identify this just with the local homology. Yeah, I think that something like this would work. I'm not 100% sure this is the correct argument, but a junction plus using the local homology already our pet module would save the situation. Like we have this. Okay. Do you agree with this for now?
Yes, and we use that. Do we use that our hat is ideal?
Yes, our hat is ideal, definitely. Yeah, okay. So, but well, probably it's wrong, but I still want to know if answer the question if I implement this rule, do I get epimorphism on the bonds? Because if I can get this, it will be not a good, but I think it's an interesting question, independent question. Okay, so that was the first proposition in the sequence of propositions that I want to show. So I think it's time for a break, so let's continue after the break. Должен успеть. Все, что я думал. Я когда продумал тест этого утверждения, то он очень сильно не сразу сошелся, но вроде с одной стороны тогда очевидно, практически, а с другой стороны как-то правильно все сказать, не очень получается. Но считаю, что здесь надо не сказать, что здесь важно, что уже как бы есть конечно порожденный модуль, выполнение которого дает дуализирующий, потому что, как мы уже договорились, наш полный модуль всегда есть дуализирующий, дуализирующий механический. Всегда есть канонический, совсем не обязательно означает, что до выполнения нашелся какой-то канонический метод. Так, попробуйте я использую перерыв, чтобы сказать пару слов про литературу, терминологию. Ну, так мы докажем теорему, что канонический модуль то же самое, что дуализирующий. Довольно часто в литературе люди имеют в виду там одно, пишут другое. Я думаю, что то, что я назвал дуализирующим, в русской Херцега почему-то называется каноническим. Но, в общем, это в любом случае понятное понятие, по крайней мере, формоформным концом. Вот. Я решил, как эти два понятия разделить. Для меня первый думаю, кто канонические модули отличает от дуализирующих, потому что у них формально определение разные. Потом мне кажется, их поэтому при чтении всяких книг стоит иметь в виду, что называть одним словом, имеет в виду другое. Да, и сейчас я хотел сказать, что можно такое прочитать такое мысль, что, во-первых, можно прочитать мысль Герцога как такую чисто альтернативную точку зрения. Я вообще его не следую, у нас наверное очень мало пересечения. Как бы я что сейчас буду делать? Я сейчас ввожу канонический модуль и буду доказывать его свойства. А он будет, грубо говоря, дуализирующий модуль, называют его каноническим, и доказывать его свойства, но более-менее похожий способ. Чуть отличается, но уже очень близко. То есть, исходя из разных направлений, просто доказываются одни и те же свойства. Ну, соответственно, я потом буду доказывать, что это одно и то же, а он, соответственно, будет доказывать, они будут доказывать, исходя из определения дуализирующего модуля, просто утверждение вот так двойственности, а из него уже более-менее ясно, если я поставлю себе очень ясно, что любой дуализирующий, если локальный двойственность у нас дуализирующий, то дуализирующий экономический. Вот. И недавно вышла книжка в 2018 году. Она называется что-то типа Chapter Homology, Local Homology, Conclusions, какая-то перестановка этих слов. Такая довольно толстенькая, там 350 страниц, там всякие разные детали про эти вещи написаны. Ну, вот я думаю, что на сегодняшний день это, возможно, самый лучший источник, если брать книжки. Вот. Но на самом деле, под конец второй лекции мы увидим, что когда начинается работа с дуализирующими модулями, то это все вот в рамках коммутативной алгебры, честно говоря, не то, что очень хорошо работает. Там нужно по-настоящему работать с активными комплексами, нужно работать с производной категорией, и тогда как бы, концептуально становится картина гораздо яснее. У нас производных категорий в курсе не было, и, в общем-то, требует отдельного курса скорее. Поэтому так у нас не получится. Но если вам хочется посмотреть, как локальные технологии работают в терминах производных категорий, можно посмотреть обзор Лихмана, ну, как это называется, блоков Homological, блоков Pavlov, еще что-то такое, текст 2000 года. И там, на самом деле, из этого обзора можно вычленить, если так посмотреть, какие там локальные технологии свойства, можно вычленить, что утверждение локальной двойственности для дуализирующего, в общем случае, комплекса уже. Это вообще какая-то логическая тавтология, там логически нет доказательств. То есть, если такой, с точки зрения производной категории, для дуализированных категорий, там натурально практически можно сказать, что это очевидно. Поэтому так правильно контекст всей этой теории.
Здесь в последнем равенстве в правой стороне, там слева это adjunction, а справа как получилось, что локальные когомологии пополнения заменились на произведение обычных с пополнением.
Это мы доказали в прошлый раз. У нас было такое свойство для любого плоского расширения.
Да, то есть что
Это я уже использовал это первую часть доказательства. Вот когда я переходил от меня был хом, да, там в середине написано. Вот сюда я перешел. Это то, что мы доказывали в прошлый раз. Вот для любого плоского расширения у нас получается цифра пополнения тоже работает. Да, еще на что есть, пока у нас такое неформальное немножко обсуждение, на что можно обратить внимание, что все, что я делал над Homological кольцом. Да. Естественно, могу спросить, как это все делать от производного параметрного кольцом. Но это вполне можно делать, только тогда дуализирующий модуль становится не модулем, а комплексом. Это называется дуализирующий комплекс. Но вообще, как бы, я немножко про это еще скажу, когда я веду определение. Вообще, первое определение надо в книжке Харскорна производительной дуалити. Вот тут идем. То, что Григорий диктовал на семинаре, видимо, направление дуализирующего комплекса. Ну и там оно несколько более естественно выглядит в контексте, опять же, производных категорий, это просто такой другой такой функции, который устанавливает то, что производная категория, скажем, ограниченная с корректными технологиями, эквивалентная двойственная. Такая двойственность — это просто архон в этот дуализирующий комплекс. То есть в каком-то смысле получается дуализирующий комплекс — это то, что позволяет сделать любой такой достаточно маленький комплекс просто рефлексивным. Что довольно любопытно свойство самого симметрической категории. Потому что определение дуализирующего модуля, когда там у нас коммутативная алгебра появляется, что такое дуализирующий модуль? Это конечный модуль, который максимально входонаходливый, типа 1 конечной эффективной размерности. Просто из определения совершенно не ясно, почему нужно рассмотреть такое определение. Это будет довольно странно. Вот оказывается, что если посмотреть, как у Харскорна сделано в дуалите, сначала оказывается, что есть просто общие такие категорные характеризации, дуализирующий модуль, дуализирующий комплект более общий, которые на самом деле можно свести к локальному кольцу, от локального кольца, грубо говоря, просто к полю. Если написать условия дуализации для поля, то это ровно это 3 условия, которые в определение входят. Эквивалентность этого определения скидки коммутативного категорного определения через производной категории. Это только есть доказательство Харскорна является дуалити. Вот. Ну хорошо, кажется, можно чуть-чуть продолжить, чтобы все успеть. It's a good news. Okay, so the second proposition in this sequence of elementary propositions is the following. That under the assumptions that I have is that R is Gorenstein if and only if canonical module is isomorphic to the ring R. Well, I want to say that in one direction, if the ring is Gorenstein, we already know this, more or less by the definition. And in the second direction, well, we can do the following computation. If I want to look at the x d minus k between the residue field and the ring R, take dual, and then this is, by the statement of the local duality, is the local homology for the for the residue field. Right, so this is for the residue field. But this local homology is very easy to compute explicitly. Well, this is just another example of a module of finite length. So we know the answer. This is k when the index k is equal to 0, and this is 0 in all other cases. So if we now look at the bus numbers for the ring R, we can see that this is precisely the one when I is equal to the dimension and 0 in all other cases. We call that the bus numbers is just the dimensions of these spaces. So hence this is a Gorenstein ring. Well, in fact, we don't even need this answer for these bus numbers. It is for us it would be to know that some bus number with a high index is 0. Definitely this follows from the local duality for the module k, residue field k. Okay, so next proposition. If element x, of course this is in the maximal ideal, so if x is R regular, then the same element x is k sub R regular, so regular on the canonical module. And quotient of the canonical module by the x canonical module is canonical module for the quotient ring. So proof. So without loss of generality, I can assume that the ring is complete. Now I look at the exact sequence, R multiplication on x, quotient by x. Let me denote this R1 for shortness. Notice that this R1 is Cohen-Macaulay, since the quotient by a regular element of Cohen-Macaulay is Cohen-Macaulay. So we have the following sequence of local cohomology. So h with the index d minus 1 of R1 is mapped to the h with the index d of R is mapped to the hd of R, and then 0. Okay, because the rest are just 0 modules, right? For the Cohen-Macaulay modules, there are only one non-zero local homology, namely local homology that lives in the dimension. So there is nothing else in the local exact sequence. Now I can apply the matless duality to this and get the following. Say 0 hd, so this is m in m, hd sub m of R dual is mapped by multiplication on x, hd sub m of R dual, and here we'll get hd sub m of R1. 0. So we know that this way we can identify with the k sub R, so the canonical module, in the same here. So this map is multiplication on x. So the quotient is k sub R module a x k sub R.
why on the left in the should exist in the first should exist sequence? Here we have 0.
Well, because as I said, if you look at the local cohomology of Cohen-Macaulay module, Cohen-Macaulay ring, then the only non-zero position is where you have dimension. All other are just 0.
Yes.
So this is the only 3 positions where we have non-zero local homology. Okay, so here we have kind of these 2 short exact sequences. For the top one, we know that the quotient is this local homology for R1, and for the short exact sequence on the bottom, this is this thing. And since these are isomorphic, this is commutative, we can conclude that we have isomorphism here. And also, I'm claiming that this is a regular on the canonical module. Well, clearly this is regular since multiplication on X has no kernel. Okay, so another proposition. So if dimension of R is equal to 0, so it's a Artinian situation, then we actually already know what the canonical module is. In this case, this is just the injective half of the residue field. Now this is another very simple proof. Dimension of ring is 0 can be currently formulated as the length of the ring is finite. So again, computation of the local homology is very simple. And this is R that lives in degree 0, and this is 0 in all other degrees. So K sub R, which has to be, well, this is of course the 0-dimensional case, it's automatically a complete case, so I can as well write this as the zeros homology with the dual. And since this is just R, the dual is the injective half. Okay, next proposition, which is just a composition, okay, combination of the previous 2 propositions, so doesn't really need a separate proof. So if X is a system of parameters, so it's 1 up to D is a system of parameters for the ring R, then canonical modular the ideal generated by the sequence times KR. KR is isomorphic to the injective half of the residue field over the ring, which is quotient by the system of parameters. So the proof was clear by the 2 previous propositions. Okay, so next elementary proposition, we can compute the bus numbers of the canonical module, and we will get that this is 1 when the K is equal to D, and it is 0 in all other cases. So as you can see, from the point of view of bus numbers, the canonical module behaves like a ring in the Gorentzian situation. Well, the proof is very simple, since we, for canonical modules, will more or less by definition of the canonical module have a local duality. We just look at the X D minus K between the residue field and the KR with the local duality. We can identify this with the local homology of the residue field. And the local homology of the residue field, we know how to compute. Just the same computation, but you need to replace R with K. So we know the answer for the right hand side, and we know the answer for the left hand side. Okay. Next one. local cohomology, top local cohomology of the canonical module is precisely E. Well, in fact, we can say a little bit better. There are no other local cohomology, only local cohomology in degree D, the rest is 0. You can see from that. Well, we take E with the bullet to be minimal injective resolution. And then we know that we can compute local cohomology using this injective resolution. So this is HD. But now, what I will get when I apply this functor gamma m to this minimum objective resolution? Well, remember when we apply gamma m, well, in each term, minimum objective resolution is the sum of the indecomposable objectives, which is just injective house of the R module. But when we apply gamma m, all these things goes to 0 except of the injective house of the K itself, right? So in this whole complex that we have here, only it survives the terms where we have the injective house of the K, right? But we have injective house of the K, well, we can look at the corresponding beta numbers, right? So this is tells that where we have injective house of the K. We have the only one injective house at the position D. So yes, it will be zeros everywhere except one position where we have, I'm writing with the bus number just to remind you the structure of the minimum objective resolution, but of course this bus number is just one. So this is the whole complex. So of course this is D. So this D is supposed to symbolize position in which this module is in the complex. So you can see that actually a little bit more is true, not just the top cohomology is the injective house, the rest of the local cohomology of the K is 0. And I want to mention that in this computation, all the information that we used about this canonical module is just what are the beta number, what are the bus numbers, right, to get this answer. Okay, and the last proposition in this sequence of elementary properties of canonical modules, it says that the endomorphism of the canonical module is isomorphic to the ring as R module. So I'm not claiming that this is isomorphism of algebras, just modules. Okay, so let's look at the home from K sub R to the K sub R with a dual. By the local duality, I can identify this with the HD sub M of the KR, right? So this is just a statement of local duality for the index K equal to 0 and module which coincides with the canonical module. Now we know that this is the injective hull. So we can say that the endomorphism of the K sub R completion, right? If I apply one more modulus duality to this identity, on the left hand side I'll get completion, on the right hand side I'll get completion of the R. But now this is a situation where I have to finally generate modules. Well, K sub R is finally generated, hence its endomorphism ring is finally generated module, so the completions are isomorphic. So by this proposition that we proved on the previous lecture, the conclusion is that the endomorphisms, the K sub R, are the same as R. And if you just look at the statement a little bit more closely, you can realize that this isomorphism is given by the canonical map. For any module, there is a canonical map from the ring to the endomorphism of this module. So in this case, this will be an isomorphism. Okay. So this finishes this sequence of elementary properties. Now I want to prove a couple of less elementary things. So theorem, let Sn and Rm be local Cohen-Macaulay rings, and suppose we have F mapped from S to R, so this is the local homomorphism. Of local rings, such that R is finite S module. Well, for shortness, probably it's better to say finite local homomorphism, but to be understood precisely, I wrote this. Okay. Now, if S has canonical module. So now we're moving to the question about the existence of canonical modules. In particular, you can kind of, in this case, algebraically speaking, push it forward along the local homomorphism, such finite local homomorphism. So we have canonical module for S, then the next H between the R and the KS is the canonical module for R, and here where H is the dimension of S minus dimension of R. Proof. Well, first of all, if we look at this X with the index H, but any other index really, so is finite S module right, finite S module, and structure of R module. So this structure comes because the first argument is just R. We can multiply this X on the elements from the R. Now, using the fact that R over S is a finite module, from this we can conclude that it is finite R module. So let me fix some notation. Let me say that E sub S is the injective hull of the S modulo M, and the E sub R is the injective hull of the R mod M, and also D will be dimension of R, and the little s will be dimension of the ring S. So unfortunately, for this proof you will need the lambda, but I kind of organize this in the wrong way, so I'm going to use lemma in the proof and then prove this lemma after the theorem. Okay, so let's look at the Hom over S from some finite R module. So let's say M is finite R module. Now look at the Hom over S. Yeah. So if this is R module, I can look at this as an S module, and let's look at the Hom into the ES. Well, Hom over S. This is M as a product is R over R. ES. Use the adjunction to write this as the Hom over R. M Hom from S over S from R to the ES. While the last Hom is precisely ER. So this Hom over S is just the ER. And this will be the lemma that I'm going to prove after the theorem. So at the moment, let's just use this. Okay, so this is just a general property for any finite R module. Now let's take a special situation when M is equal to the X with the index H, R, K sub S. So then, for this module, you'll get the following. You'll get Hom over R, X, H, in R, S. So homing this into the injective power of the residue field. Okay. Now we know that this we can replace with the Hom over S with the same X. But this will be, the second argument now will be the injective half of the residue field over S. This is by what we proved before and by the lemma that I'm going to prove after the theorem. Okay, to this thing we can apply local duality over S and identify this with the local homology with the index N, index D. Check me that the index is correct. So this is indeed D, N, R, right? Now by the statement, which I call the base independence, this I can identify with the HD and R over R, or the extension of the AT, which in turn can be identified with the HD M of R, right? Which is everything here is true, this is essentially the end of the proof, right? Now, I think the only thing we need to understand is that how we get this isomorphism. Y and R, so homology with respect to this ideal is the same as a local homology with respect to this ideal. Well, and this follows because, so let me say, the last isomorphism follows from the fact that the NR is M primary. Right? If NR is N primary, then the local homology are the same. And why this is M primary? Well, if you look at the R modulo NR, I can as well present this as an S modulo M, then the product over S with R. Right? That's just a general property of tensor products. Then take a tensor product of some module with a quotient trick. You will always hear this. But what we can say about this quotient? R over S is finite, right? This is just a field. So here what we have is some finite dimensional vector space over this field. So if this is finite dimensional vector space, this is Artinian ring, right? Hence the dimension is 0. So the dimension of this thing is 0. And this is only possible if the ideal is imprime. So this quotient is Artinian, hence necessarily, and R is imprimer. And that's the end of the proof. Modulo this lemma that the home over R from R to the injective hull is injective hull for the root R. Maybe I just erase that whiteboard. So lemma. So in the situation as before, but maybe even I can drop coin or call it. So just let's not let this as lemma. Let phi be a finite local homomorphism of local Noetherian rings. So then the injective hull of R is isomorphic to the home over S R injective hull S. Okay. Proof. So first of all, we need to notice that this home that we have in the statement is actually injective R module. And for this we can see that the functor home over R blank this home, which by the home tensor adjunction can be written as the home over S blank ES is exact, right? Well, the functor on the right hand side definitely is exact, so the original functor is exact. And what I wrote here is the home tensor adjunction. Well, they're supposed to be a tensor product, but this tensor product here is over R with R, so we can as well just don't write anything. So this means that this home is injective. Let me write this. Home over S R E S is injective. Injective R module. Okay. The next claim that this home over S with the R E S is Artinian S module and hence Artinian R module. Okay, I think this is clear, right? So this is Artinian as the matrix dual of finitely generated Noetherian, and if this is Artinian as an R module, well, you can consider this descending chain of submodules of R modules. Then this will be, if this doesn't stabilize as an R modules, this doesn't stabilize as an S modules, so this won't be Artinian as an S module. Okay, so now from these two observations I claim that I can write this home over S RES as the injective hull of R to some power n. right? Well, this is because this is injective. So for injective modules, we have this structure theorem, which says that this will be the direct sum of such injective hulls. But this is also Artinian, and we know that Artinian has to be a submodule inside module like this. Hence, the only possibility is that we have only several copies of the injective hull of the residue field. So now we only need to prove that this n that we have here is equal to 1. And for this, I have a sequence of isomorphisms. So I have the residue field k to the n, which I can compute as the Hom over R from the k to this module. Right, so this is kind of like n copies of the matrix dual of k. Now, to this, I apply the, again, Hom tensor adjunction to write this as a Hom over S, k tensor product over R with R, which is just doesn't do anything, E sub S, okay. Now, again, another Hom tensor adjunction. Maybe the way I do this is not the most optimal way, but this is what I was able to find when I prepared the lecture. So Hom S L E S. So here L is just by definition S modulo n. Okay, so if you look at this Hom and apply Hom tensor adjunction, you'll get precisely this Hom. No, you can just erase this R.
How we get the last isomorphism?
This one?
Yes.
Yeah, I'm just saying this. Look at this Hom and apply to this Hom Hom tensor adjunction. So then you need to write this Hom, but instead tensor product with R over R, you get L and L. So as well, you can just cancel R over R, L over L. Okay. Okay. Okay, so finally, yeah, of course, now this second argument, this is matrix duality over S, so this is just L, so what we will get is Hom over L from K to the L, which we can identify with the K. So n is equal to 1. So in this case, K is a finite dimensional L vector space. So of course the dual could be identified with the same space, but what's important that this is just one copy of K. Okay, so from this I can derive a couple, actually 3 corollaries. All of them are quite elementary. So first one, if R is S modulo I, and S has canonical module, then we can kind of move this canonical module to the quotient. It is canonical module over. So here I'm just choosing the fact that if we take a quotient, then this is a finite local map. So corollary 2, if of course in this case to be in the correct situation I need to assume that S and R are Cohen-Macaulay. So if a local Cohen-Macaulay ring R is a quotient of a Gorenstein, then R has a canonical module. So we don't know that any, and this is just not true, that any Cohen-Macaulay ring has a canonical module, but the quotients of Gorenstein rings have canonical modules. Or I can also write corollary 3, but you can understand this already. So any complete Cohen-Macaulay local ring has a canonical module. So the idea here is that if this is complete, by the coin structure theorem, this is a quotient of a regular ring, and regular ring is Cohenstein, so it has canonical module. Hence, in this situation, this is complete Cohen-Macaulay, then it has canonical module. So all three corollaries are completely elementary. Okay, what is interesting is maybe even surprising that this corollary 2 actually works in the other direction. So local Cohen-Macaulay ring has a canonical module if and only if this is a quotient of a Cohenstein ring. So this is our next goal, next theorem, and this is based on the construction of the extension. So construction.
Is it true in corollary 3 if we delete the condition about Cohen-Macaulay? So does?
Well, if this is not Cohen-Macaulay, I don't even define the notion of canonical module. If you look at the definition, I define it only for Cohen-Macaulay rings, and then I derive local duality for Cohen-Macaulay rings.
Yes.
But yeah, you can remove this Cohen-Macaulay condition, but you need to work with dualizing modules and replace them by dualizing complexes. This is what I want to say at the very end of the lecture. Okay, so construction of extension. So this is construction that we're going to need in the proof of the next theorem of a ring by a module. So this is just a quite general construction, but usually you see this construction as something like deformation theory. Here I'm just going to give you definition and summarize its main properties and leave this as an exercise. And I believe this is quite easy exercise. It's more like, you're not even Commutative algebra, but maybe like in first year algebra. So here I have R is a commutative ring. M is an R module. Quite general construction, don't need too much at the moment. So then the ring, I'm going to call this R star M. Sometimes you can write this symbol like for semi-direct product of groups, but star just might be way easier to write on the blackboard. So the ring has R plus M as R module. So the ring is this just direct sum as R module. And multiplication is given by the following rule. So if I want to multiply Rm times Sn, then this is Rs, Rn plus Sm. And a little bit twisted multiplication of the second summons. So you can check immediately that this is actually another commutative ring. In this commutative ring we have an ideal, so I, which is just 0 plus m, so all the elements where the first component is 0. So this is an ideal, and we can check two properties of this ideal. If you take R star m and take a quotient by this ideal, you'll get ring R. And also, easy to compute that the I squared is equal to 0. So when you talk about extensions of the ring by modules, usually people talk about the square 0 extension. So this is an example of the square 0 extension, okay, the canonical example. But there is another one where we have trivial multiplication, but this is canonical example with non-trivial multiplication. There are of course other extensions, but not given explicitly by some formulas. They just can show that there are other, in some cases, of course. In some cases, there are only trivial ones. Okay. Now I have a list of properties. So if R is Noetherian, and M is finite, then this extension is also Noetherian. So this is Noetherian ring. So second dimension of the R star M is the same as the dimension of R. So if R is, say, Rm is local, then R star large M is local, and the maximal ideal, so the maximal ideal little m plus large m. So, and the last property, last exercise, is that the depth of this R star m is the minimum of the depth of the R and the depth of m. So the last one is, well, it's not hard, but I think the first three is very easy exercises for the first year algebra. The last one is really commutative algebra, like in this course, but I'm not going to use the last one. So these are 4 exercises. So finally, theorem. If a local Cohen-Macaulay ring R has a canonical module K sub R, then R is the quotient of a local Gorestan ring. Okay. So now the proof is actually quite easy when we know this construction and all the extensions. So we just set S to be R star KR. So we extend the given Cohen-Macaulay ring with its canonical module. So then we have the following situation. We have R, which is always mapped to the S. So in this case, this is a finite local homomorphism. And then from S, we have mapped back to the R, which we can identify with the S modulo I. Okay, so now S, in a topological way as a module, I can write as a home from K sub R to the K sub R. Well, this is just the R itself, plus home from R to the K sub R. So indeed, this is a copy of R and the K sub R. So this is for modules. So now this isomorphism I can write as the home from the R plus K sub R to the K sub R, right? Just additivity of the home function in the first argument, which is S, right? So this is home. Of course, all these homes are over ring R everywhere. So this is home over R from S to the K sub R. Okay.
Why this is so?
What exactly?
For example, the first isomorphism. Yes.
Well, this is R. We proved among these elementary properties that the endomorphisms of the K sub R is R.
Yes.
And this is just K.
Yes.
So this, as a isomorphism of modules, this is fine. Okay. So, but yeah, but now we can see that this home, since we know that the dimension of the S and R is the same, so this home is exactly that XH, where H is equal to 0. So this thing is the canonical module for S. So this is canonical module for S, right? By the previous computations. But we can see that the canonical module for S is actually isomorphic to the ring S. Hence, the ring is Coniston, right? And the rest of the properties are easy, right? So we know quite generally that this is local, and we know that R is a quotient of this thing. So I want to say that this then finishes the proof. Okay. So finally, the last section, 545, dualizing modules. So definition, let Rm be a local Cohen-Macaulay ring a dualizing module is finite R module omega such that first omega is maximal Cohen-Macaulay, second the injective dimension of omega is finite, and third the type of omega is 1. As I promised, this is a little bit weird looking definition, why such a module is an interesting object. Well, if we look at the definition,
Can you recall what is the rank?
well, the ring, the type, this is type of the
What
module.
is the type?
Well, you do the following. You just look at the text. Well, generally, you need to write D here, which is the depth. But in our case, the depth is the same as dimension, so this can be, you can think about this as dimension. So this thing has to be K. So here D is dimension of omega of the depth of omega. Okay, so two remarks. So first remark, omega is dualizing if and only if we have the following properties of the bus numbers of the omega. So there is only one non-zero bus number, and this bus number is equal to 1 at the dimension of omega, and the rest are just 0. As you can see that the bus numbers, well, remember the bus numbers are just dimensions of this X, right? So the bus numbers beyond the dimension are 0 because the injective dimension is finite. And if the injective dimension is finite, it is equal to the dimension of this. Yeah, it is equal to the dimension of this module. Right? Now, below the D, there is no such X because this is Cohen-Macaulay. By the Riesz formula, there are no X for the index less than D. And when we look at this X, I, when I is equal to D, because the type is 1, you get that this bus number is 1.
And in general, the K is some degree instead of K.
Here?
Yes.
Depth in general.
Yes, but on the right hand side of this equality. In general, there is no K, but K in some degree, right?
I don't understand this.
If omega is arbitrary module.
Yeah, so then if I want to say what the type is, I want to put here depth
Yes.
and look at the dimension. This is the type.
Over K.
Yes, okay.
And it is a vector space over K.
Yes, because the first argument is just K. Okay, so this is first remark, and the second remark, any canonical module is dualizing. Right, since we know that being dualizing can be expressed in this result of the bus numbers, we know that this result for bus numbers is true for any canonical module. Hence we have this. So it's not even the theorem, it's just immediate observation. Okay. Now, let's prove a theorem, which is kind of a very special case of a more general theorem that actually indicates why such a module, or maybe even before this. Maybe even before this. Well, as a short remark, I can write this in the following way. If I look at the functor R home, right? Say if I want to apply this to the K, and this is omega, then this will be K that sits in degree T. Right? So I'm just rewriting more or less remark 1, but using R home. It means that this functor R home with the blank as the first argument and the second argument is omega, if this is true for the K, well, it will be some kind of duality, contravariant duality, for the, at least for the finite length modules. So more or less by definition, this gives us a duality for finite length modules. And in fact, this is duality for some quite general complexes. In particular, this is duality for the finite generated modules. So let's try to derive this. So let R, okay, so let R be a local Cohen-Macaulay ring with dualizing module omega. And then for any finite R module M, the canonical evaluation map is quasi-isomorphism. So the evaluation map from the M to the R home M omega. So
what is R home?
well, the correct definition will be in the derived categories, but we can think about this naively. This is the whole complex that you obtain, for example, if you replace omega by injective resolution.
Yes.
You get complex that if you compute cohomology of this complex, you get X. But here you need to actually work with both complexes.
So it is a complex.
Yes. And this is the first indication. Even if you want a result for modules, you actually need to work with the whole complexes, and you actually need to work in the derived categories to get kind of understandable and reasonable proofs. So here is kind of what I'm going to do is just adaptation of the reasonable proof to the tools that we have in this course.
Yes, and after applying at home the second time, you applied for two complexes.
Well, you can think about this way. You take omega, right? You fix an injective resolution, so I with the bullet. Then this thing is just precisely home from the home M, I with the bullet, I with the bullet.
Yes.
So by choosing resolution, you can think about this way. Yeah, and the claim is, well, this is of course form in the complexes, so there is also bullet somewhere here. So this will be a complex, this will be another complex. So if you take a homology of this complex, you'll get precisely this.
But on the left-hand side, it's the module.
Yeah, but it's as a complex that sits on degree 0 and the first major 0. Okay, proof. So I introduced two functors, two family functors. Ti of M will be, by definition, the cohomology Hi of the right-hand side. So R home, M omega, omega. And the second family of functors Si is much easier to define. So this will be M when I is equal to 0 and 0 for positive I. So this is I non-negative in both definitions. Okay, so I claim that Ti of the residue field is the same as Si of the residue field. And this is more or less the definition of the dualizing complex that gives us this equivalence for any I, non-negative. Now from this, by 5 lemma, we can say that we have such an equivalence for any module such that the length is finite. Meaning that if you have the short exact sequence of finite length modules, right? For example, if you know this for length 1, you want to show this for the length 2, length 2 in the middle, length 1 in the beginning, and then at the end. You have the short exact sequence applying this functor and this functor. Of course, for the second one, it's kind of trivial. I give you the long exact sequences. So you get isomorphisms in, say, in two positions, and in the middle you also get isomorphism by the 5 lemma. So this is not very hard to show, so I'm not going to go into details. So then we continue by induction. By induction on the dimension of M. So we have the base of the induction. The base of the induction is dimension 0, which is finite length modules. Now I do the following. I consider some module M prime inside M, and M double prime is the quotient. So M prime is the maximal submodule of finite length. Okay, so then the dimension of the M is equal.
In what sense it is the maximum?
No, in the sense that this is not a ring, I have a family of submodules, so there is a maximal element. I take any maximal element. So, yeah, so this is a finite length, so it is supported only on the maximal ideal. The same reason as we used in the beginning of the today's lectures. Dimension of M is the same as dimension of the M double prime. And also, M is not associated to the M double prime, right? Because if the M is associated to the M double prime, it means that there is a copy of K inside M double prime. It means that the M prime wasn't the maximum. So M is not associated to the M double prime. It means that there is a regular element okay, so And, yeah, so if I want to do induction by the dimension, I can say that without loss of generality, right, I can go from m to the m double prime, and the dimension is the same. So without loss of generality, we can consider m such that m is not, maximal is not associated to the m. So there is our x in the maximum ideal regular on the module m, and we get a short exact sequence, the standard one, m, x, m, m1, which is by definition m modulo x, m. So then we have the following diagram. So we have S index I minus 1 for M1. We have Si for the M, X, Si for the M, Si for M1, and the same for the T. So from the point of view of homological algebra, the correct terminology is that T and S are not just family of factors, but these are two delta factors. Meaning that for a short exact sequence, you get this long exact sequences with connecting homomorphisms. For example, for any derived factors, you get those. So for the second one, it's kind of trivial, and the first one is a derived factor. Okay, so by the induction hypothesis, these two are isomorphisms, and we have, of course, maps here, right? For dimension, for the module M1, since this is of dimension, say, d minus 1, we have the statement. So we only need to show that from this diagram, we can conclude that these maps are. Yeah, maybe I also need to fix some notation. So this kind of, we have this canonical, not just a family of factors, but we have also canonical maps. Let's call this theta I of m. So this is theta I of m, and this is theta I of the. So this is isomorphism. Theta I m1, and this is theta I minus 1. So this is just the names of this natural transformation between two factors, between two family of factors. Okay. But if you look at this diagram, you can notice the following, that the kernel of the theta I of m, and there is a map induced by multiplication on x, kernel of the theta I of m, 0. So this is kind of more or less the last observation that we need to finish the proof. Do you see that we have such diagram, exactly on the right? Let's work. Reasoning with the snake lamb or something like this, right? We will have kernels that are submodules here and here, right? So then there is the map of the kernels is clearly induced by multiplication of x, and there is no kernel here. So through this little diagram change to get this. But from this you get immediately that the kernel of the theta I of m is 0, right? Because this is another application of Nakayama's lemma. And you can do exactly the same thing for the co-kernels. Repeating the argument for the co-kernels, you get co-kernel of the theta I of m is isomorphic to 0. And that's all we need. So this theta is isomorphism for any I, and for any finitely generated module. Okay. So this is kind of shows us why it is reasonable to call such M with such definition dualizing. Now, essentially, the last ingredient of this course, I can say, I want to show that module is canonical if and only if this is dualizing. And to do this, I need the following lemma, which is kind of the key technical ingredient in the proof. So let R be an Arthusian ring. We have some ideal I. M and N are finite. Are modules. So then we have the following. First, if you try to compute the gamma sub I on the home, then you get surprising property that this is the same as the home from the M to the gamma sub I of the N. You kind of move this naturally to the second argument. And then second statement is that you can derive this. So R gamma sub I of the R home between M and N. Of course, in the reasonable theory, M and N could be replaced by some complexes and get identity for derived functors. So this is R home M R gamma I N. So this is of course quasi-isomorphism. Maybe I need to use another notation for quasi-isomorphisms, I guess. Okay, proof. The first one, well, to show the first one is kind of more or less standard computation. Well, it is clear that we have this when M is equal to R. It is clear, right? The right hand side and the left hand side is the same. Now, if I have more general M, I just take a free presentation. So choose a free presentation of M, and do the standard thing with the 5 lemma. So then I'll get 0 gamma sub I home M N gamma sub I home F0 N gamma sub I home F1 N. So I choose the free presentation, applied the left hand side first, then I can apply the right hand side first, then I'll get for the right hand side home M gamma sub I of N home F0 gamma sub I of N. Okay, so of course for free modules these two terms are isomorphic. Now also we can easily understand that there is a canonical map from the left hand side to the right hand side. Well, we can obtain this map as follows: gamma sub I of the home M and N. It is clearly embedded as a submodule just into the home of the M and N. M and N. Right? And then there is a map to the home from M to the gamma sub I of N. Right? And this last map So this is induced by the embedding of the gamma sub I n into the n, and then to this embedding I apply the Hom with the first argument m. Right, so this is contravariant factor, I'll get the map in that direction. So there is this composition which gives me this canonical map here, and clearly this composition is an isomorphism when the m is a free module of finite rank. So by the 5 lemma, anyway, this is an isomorphism for any module. 2. So we take P of m to be projective resolution, and we take I to be injective resolution of n. Choose 2 resolutions. So then the gamma sub I of the Hom E and I, we can identify this with the Hom E gamma sub I. Right. Well, if you have this is precisely formula 2. Right? If I want to derive functors, this is what I'm doing, replacing object with these resolutions. There are several small things that you need to understand here, which I'm not going to maybe spend too much time on this. Well, on the right-hand side, there are no problems, right? So you clearly derive the gamma functor, you clearly derive the Hom with the projective resolution. Here, there is a question, right? So if I look at this Hom complex, why this is a resolution for the argument for this Hom, right? So I'm supposed to put injective resolution for this Hom, right? So this is just Hom complex. Well, this is more or less easy to see that when you write a Hom, it will be some product, right? But the product will be finite. This follows because the projective resolution is bounded on the right, injective resolution is bounded on the left. So here in the Hom it will be only finitely many terms, all the terms will be injective modules, and indeed this complex will be quasi-isomorphic to the Hom. Exercise in homological algebra. So this is...
What do you mean by applying gamma sub I to a complex?
No, that's another reasonable question. Well, because if you want to do this reasonably, you kind of want to extend all the functors, like x functors, local homology, and everything to the complexes. So in this case, well, wait, no, that's not a reasonable question. This is a silly question. I'm applying this to a module. Here I'm applying this to a complex. Yeah, here I'm applying this, yeah. Here indeed, so I have this complex. So, and I need to replace this by the injective resolution. And in fact, there are problems here. You can only do this if the complex, if you want an injective resolution, this will work only if the complex is bounded on the right. Then you can replace this by the injective resolution. And if this is not the case, you can replace this by the K injective resolution, which is just something from the right orthogonal to the acyclic complexes. So you see here we can go into actual reasonable homological algebra, where you need a little bit more than the basic courses. But I'm claiming that if you just look at this particular complex, this will be a resolution for the Hom. So it will be a complex of injectives quasi-isomorphic to the Hom. And in fact, this will be K-injective resolution. So this is a problem. If you want to do this in a simple, understandable way, you need to extend everything to the derived categories. All functors has to be functors of complexes after quasi-isomorphism. But unfortunately, it's not possible to do in the same course. Cohen-Macaulay, Cohen-Stein rings, etc. And also reasonable homological algebra. So it has to be separated into 2 courses. Okay, so maybe think about this as a kind of half a survey, kind of steps, right steps without right explanation. But what you get here is just well, you believe in this formula, and this is precisely formula 2. So this can be extended into complexes. So finally, I'm almost out of time, so let me derive the final theorem. So let R be a local Cohen-Macaulay ring, a finite R module. I'm going to call this D because I cannot choose notation K or omega, so K is standard notation for canonical, omega standard notation for dualizing. D is also another possible notation for dualizing something. So finite R module D is canonical if and only if it is dualizing. Okay, so proof in one direction. If this is canonical, then this is dualizing. We done already. This was remark 2 after the definition. So we only need to prove that any dualizing is canonical. Okay, so in the lemma, we can take M is equal to N and is equal to this D. So, and then we can notice that R from D to D. Now I assume that D is dualizing in this proof, right? So R from D to D is R. Well, we have done this computation this is obvious. Right, so this is a module, and we look at this theorem that the evaluation map, canonical evaluation map, is quasi-isomorphism, and we just plug in R as an argument there, right? So then you'll get that R is quasi-isomorphic to this R, so this is quasi-isomorphism. Okay. Now, R gamma sub I sub M in this case, sub M of D. This is isomorphic to the E shifted by D. So we've done this computation for canonical modules in that list of propositions. But actually, the only thing that we used to do this computation was our knowledge of the bus numbers, and the bus numbers of D are precisely the correct ones. So for dualizing, this we also get knowledge immediately by replacing D with the minimum objective resolution, and we get this answer. So if you now look at this lemma, so this will be R gamma of the R, and this will be dualizing, and this will be just maybe I just need to write this. So if you do this, we'll get R gamma sub I of the R, right, because R home from D to G is R. Then on the right hand side, we'll get R home. Now the first argument is D, and the second argument, well, this is just E that sits in degree D. Of course, the R home, since the second argument is injective, is the same as the home. So this is home D E that is shifted by degree D, and this is just D dual shifted by the degree D. Which is precisely what I need if I compute the cohomology of the complex on the left. This is the dual of D, so this is canonical. Okay, so this is the last thing I wanted to show to you. So the upshot is the following. This is kind of not completely standard way to do all these steps, because I'm first focused on the canonical modules, and for canonical modules the local duality is kind of triviality. You can get this immediately without proving anything, really. And then I introduced dualizing complexes and proved kind of independently and by using this lemma that the dualizing complex is the same as a canonical complex. So if you combine these two things together, you can notice that there's a statement of the local duality for dualizing complexes. And now you can compare this with any other proof that you can find in the literature, and I'm sure that you find that this proof is shorter and easier to understand. So, okay, so that's all I want to say. This is the last lecture. So the last assignment is due on the December 25th, and after that I'll grade it and give you the final marks. But probably, who are for you, those are in the room, you'll get 10 without any notes. For you, those are in the room, you'll get 10 without any notes.